Thanks to all the organizers for putting together this great conference and for inviting me. It's always great to be back in Santa Barbara. So I'm going to tell you about QED in 2+1 dimensions from a few different points of view that I've been thinking about with collaborators. The main reference will be this paper that I wrote with Pierluigi Niro, who was a postdoc at UCLA, and I was a postdoc at CISA, and my colleague Ryan Thorngren. And there was also related work at about the same time by Shai Chester and Zohar Komorgotsky. And at the end of the talk, I'll also mention two papers in progress with these sets of collaborators. One is about trying to translate what I'll tell you into some maybe better suggestions for what to look for in the lattice, which I'll try to mention briefly. And the other is to kind of run a consistency check on the claims we make about the non-supersymmetric theory by relating it to a much better studied supersymmetric theory by deformation and following the RG flow. So I'll try to mention that at the end of the talk. And I'm going to follow Anna from yesterday and also encourage you to interrupt me during the talk if there are questions. So this is the QED Lagrangian. I'm in 2+1 dimensions. So the psi's are two-component Dirac fermions of electric charge 1, and I'm going to have NF of them. This label I is a flavor label. And when I say I want to study QED, what I really mean is I want to study U1 gauge theory with 0 Chern-Simons level. So I have time reversal symmetry and parity. And that, together with the famous parity anomaly, requires the number of flavors to be an even integer. So I'm working in those units. The gauge field is a U1 gauge field. A is the connection, and F is the field strength. But if we are a little more precise, it's actually a spin C connection. And the reason for that is that the fermion number that rotates all the fermions by a minus sign is actually part of the gauge group. So this is actually a bosonic theory in the sense that all of its gauge invariant local operators will be integer spin operators. And that also has a bunch of implications for anomalies and things like that, but we'll see that very explicitly at the level of the operators as well. So depending on what corner of physics you're from, this theory has a different place in your heart, but it's interesting to many different physicists. For example, people started thinking about it in the context of very high temperature 4D QED in the 80s. It's interesting in condensed matter physics from the point of view of describing spin systems in the plane, spin liquids and things like that. And it's also kind of historically been viewed as a somewhat simpler analog of QCD, because it is a strongly coupled gauge theory in 2+1 dimensions, unlike in 4D, that is also vector-like and has many kind of superficial similarities, and we'll try to explore some of those. So we already heard about conformal windows from other speakers, and in this talk I'll be interested in the conformal window of this theory. So the theory is labeled by essentially just one parameter, which is the even number of flavors. If there are no flavors, the theory is just free Maxwell theory. And famously, if the number of flavors is large, then this theory is weakly coupled. It can be analyzed in a large NF expansion. And in that limit, one finds a weakly coupled conformal field theory, where you can compute the anomalous dimensions in a 1 over NF expansion. And that conformal field theory doesn't break any symmetries. I'll mention in a little bit what the symmetries of this theory are, and they're all unbroken in the conformal phase. So this is the conformal phase, and we know that it exists at large enough in F. As you lower in F, the theory becomes more and more strongly coupled. So we don't know how to analyze it from the point of view of perturbation theory. And one might wonder whether eventually this conformal behavior stops. It's not definitively known whether this is the case. It could be that even the lowest non-trivial NF is a CFT, but it's an interesting question. So this is the question of whether this conformal window ever ends before you get to free Maxwell theory. And this question has occupied an enormous body of work from many points of view: analytic calculations, lattice simulations. One interesting hint that I would like to kind of pick up on comes from more recent explorations of this theory using the conformal bootstrap. Because if you assume that such a CFT exists, then it should be consistent with the conformal bootstrap, and you can try to put a bound on an F. And the study of the conformal bootstrap in QED was really initiated by Chester and Pufo a few years ago. And there's been kind of a steady stream of work. And in the last few years, there were some papers that seemed to give hints or suggest that the theory that has 4 flavors, so the next to minimal one, is consistent with being conformal. But the minimal theory with only 2 flavors is kind of in tension with being a conformal field theory. So these are not definitive statements, they're bounds, they're sort of suggestive, but there seems to be a difference between these two. Later in the talk, I'll also explain to you why this difference between an f equals to 2 and an f equals to 4 is natural from the point of view of supersymmetry. So what I'm going to do in this talk is I'm going to assume that this minimal theory with 2 flavors is not a conformal field theory. If it so happens that in a few years we find out that it is, then what I say here doesn't apply. And so I'm explicitly assuming that it's not a CFT. But in that case, I'm going to propose a very tightly constrained symmetry breaking scenario for what this theory can and should do. And in principle, if it turns out that the theory with an f equals to 4 or an f equals to 6 is also not a CFT, then in fact there are generalizations of the symmetry breaking scenario that also apply to those cases. But I'm going to focus on the minimal an f equals 2 case both because it's the most economical and also because it's the most likely not to be a CFT. All right. Now, as I'll explain to you in a little bit, once you assume that the theory is not a CFT, it's easy to rule out the idea that it should be a gap phase. You might imagine that it's trivially gapped, you might imagine that it's gapped with a TQFT, but this can be essentially immediately ruled out from many points of view. One point of view is just anomaly matching, but it'll also turn out to be inconsistent with the phase diagram that you get when you turn on masses in this theory. So I'll try to explain that in a little bit. So you need some kind of gapless degrees of freedom, and the gapless degrees of freedom will come from symmetry breaking. They'll be Goldstone bosons. And as I said, after I explain this scenario and try to justify it a little bit, I will mention possible lattice approaches to detecting the kind of symmetry breaking that I'll introduce. And then I'll mention the consistency with the RG flow from supersymmetric theories. The supersymmetric theories that I'll talk about are versions of supersymmetric QED with n equals 4, so 8 supercharges in 2 plus 1 dimensions. All right, what are the symmetries of this theory, since we're discussing symmetry breaking? These are all ordinary zero-form symmetries. So this is, relatively vanilla stuff, but there's a few intricacies associated with monopoles that I want to point out. So first of all, there's an SU2 flavor symmetry, which simply rotates the flavor indices, the doublet indices of the electron fields here. And then there's a U1M symmetry, which I call the monopole symmetry. It's sometimes also called the topological symmetry. And because the theory is vector-like and has no Chern-Simons level, it preserves C, P, and T separately, so that's interesting. So if you look at conventional gauge invariant operators that you built out of the fields, out of the fields in the Lagrangian, those don't carry any monopole number. So they're neutral under this U1M, and therefore they actually transform in only integer spin representations of SU2. They transform under faithful SO3 representation. And one example that will occupy us is the triplet fermion bilinear. So you can take the fermion bilinear and contract the flavor indices in such a way that you get a triplet. And this indeed transforms in an integer spin representation. Now, famously, abelian gauge theories in 2 plus 1 dimensions also have local monopole operators. So these are disorder type operators. I'll call them generically sort of M of X. They're completely local, just as local as the other ones. But they're defined by a Dirac monopole singularity at some specific space-time point X for the dynamical U1 gauge field. Okay, so one can say that in a number of equivalent ways, but this is one way of saying it. So I'm going to take a little point in space-time. I'm going to insist that near this point in space-time, the electromagnetic field has a monopole singularity, and if you want to measure the magnetic flux around this point in Euclidean space-time, then it integrates to 2 pi times an integer, which is the magnetic charge. And that magnetic charge is precisely the charge under the U1 topological or U1 magnetic symmetry of the theory, which is a global symmetry. Okay, it measures the monopole flux. Just as a reminder, let me tell you what these monopole operators look like in free Maxwell theory. Free Maxwell theory is famously dual to a compact scalar in 2 + 1 dimensions, a Goldstone boson. If I denote the compact scalar by sigma, then the monopole operators are the exponentials, the vertex operators, if you wish, of sigma, and they have charge qm. All right, so this Goldstone boson is called the dual photon, and because sigma is in the exponential, it means that m gets a vev, and therefore the U1 magnetic symmetry is spontaneously broken in free Maxwell theory. So you can interpret the dual photon as the Goldstone boson for that symmetry breaking. And we'll see a variant of this statement when we go to QED as well. It'll be slightly more involved. So in QED, we don't just have the photon, we also have the fermions. And in the presence of such a Dirac monopole singularity, the fermions, the massless fermions, have zero modes, okay, that are protected by an index theorem. And those zero modes, for reasons having to do with gauge invariance and imposing Gauss's law, necessarily dress the sort of bare monopole operators of Maxwell theory. And you can figure out which state satisfies the Gauss law, and it turns out that the state that satisfies the Gauss law is the bare monopole dressed precisely by one electron field. Since the electron field is in a doublet of SU2, the monopole operators in this theory acquire doublet indices under SU2. So the fundamental, the minimal charge 1 magnetic monopole in QED is actually a scalar field that transforms in the fundamental representation of U2. Right? It has charge 1 under U1M, and it's a fundamental under SU2. For the sake of group theory, you can think of it as a standard model Higgs field, but these are global symmetries, not gauge symmetries. The reason I mention that is because it's easy to figure out what the breaking pattern is, if you remember that. Okay, any questions?
But the sigma is dimensionless, right? This field, right?
Yes.
So you said that it's a free theory, but probably sigma is quantized in...
It's 2 pi periodic. It's an angle. Sigma is an angle. It's 2 pi. Yeah, it's 2 pi periodic.
Also, you should necessarily have singularities, yeah?
Sorry?
Monopoles have singularities.
Yes. Okay, so here's the symmetry pattern, the symmetry breaking pattern that I would like to propose for this theory. So my claim is that the symmetry breaking is essentially driven by this fundamental monopole acquiring a vev. So the original global symmetry we started with is this. And then because the monopole carries charge under both U1 magnetic and under SU2, there's an unbroken U1 subgroup. In the standard model, that would be the electromagnetic subgroup that's unbroken by the Higgs field. So we have a symmetry breaking where U2 is broken to U1, and there are 3 Namu-Goldstone bosons. Okay? Now, it's very convenient to think of the coset that's parametrized by these Goldstone bosons using the Hopf map and the Hopf vibration. So the coset is given by the usual, U2 divided by U1, and it's a squashed 3-sphere. It's topologically a 3-sphere, but it's not metrically round. It only has this reduced U2 symmetry. So that means that one of its Hopf fibers is actually squished relative to the other, but that's not a problem. That's not going to bother us. Now, you can describe both the round and the squashed 3-sphere using a Hopf vibration where the base of the vibration is S2 or CP1. And you can think of that as being parametrized by a unit vector n. And over each point of the CP1 is a circle fiber, which lives above that point. And the point is that the bundle as a whole, globally, is twisted, and so that you get a total space which is S3 rather than S2 times S1. So explicitly, the Hopf map from the monopole operators, which parameterize the whole S3 to the base, is given by forming this magnetically neutral triplet combination of the M's, and that projects you from a point on the bundle to the base space. Okay? Conversely, over each point in the base space, there is a compact sigma fiber which parametrizes the circle there. So let me just give you the example of the North Pole. The North Pole of the base is going to be my go-to reference point. If you sit at the North Pole, then the hop fiber is parametrized by this configuration of monopole fields. They live entirely, the sigma field that parametrizes the fiber lives entirely in the first component. And so that means that the linear combination of the magnetic symmetry and the Cartan of the SU2 flavor symmetry that's unbroken is this one. And this linear combination is non-trivially fibered over the base. So for example, if you did the same thing at the South Pole, you would find that the fiber lives in the bottom component of M, and the unbroken symmetry would have a plus. Okay, so when you SU2 covariantize, the whole thing becomes more complicated, but we can use SU2 symmetry to only focus on one point at a time on the base. Let me say a word about anomalies and anomaly matching briefly. This theory has a 't Hooft anomalies for its global symmetries, and in particular, it has a mixed parity type anomaly involving time reversal and the flavor symmetry. And this anomaly is characterized by a four-dimensional anomaly inflow action, which is essentially a theta angle for the U2 instanton number. I've written here C2 of U2. C2 of U2 is the second Schrödinger class, which is a linear combination of the SU2 instanton number and the U1 magnetic instanton number. Both of them are non-trivial. And this theta angle is pinned to be either 0 or pi when you have time reversal. In the case of theta equals 0 corresponds to no anomaly. In the case of theta equals pi corresponds to having a non-trivial parity type anomaly. And it turns out that the anomaly is matched in the S3 sigma model that I described on the previous slide by a conventional theta term. Right? So if you think of the sigma model fields in 3D as maps from three-dimensional space-time to the target space, which is a squashed three-sphere, then that map has a winding number. Right? There's a 3-cycle, and if you pull back the generator of that 3-cycle, omega, using the sigma model fields, then you can write a conventional theta term in 3 dimensions. And if you compute the contribution of this theta term to the anomaly, you see that this theta exactly reproduces that theta. So you have to set theta equal to pi. So the fact that we had a twisted bundle that generates a 3-sphere with a 3-cycle is crucial in order to match the anomalies in this way. Okay. Let me say a few things about the fermion bilinear. It turns out that we'll show in passing, as I go through the explanations, that the fermion bilinear, which looks a little bit like the standard chiral symmetry breaking order parameter that we're used to from QCD, also gets a VEV. And it turns out that this VEV is perfectly aligned with the sort of SU2 direction that's singled out by the Hopf vibration. In other words, if you project to the base, the CP1 base of the Hopf vibration, you already have exactly such a triplet, and it turns out that this triplet is exactly aligned with that triplet. That's good, because otherwise there would be additional symmetry breaking, additional Goldstone bosons, and I claim that there aren't any. The reason I'm mentioning this is because I'm sure many of you have heard discussions in the literature on this problem where the focus was entirely on this fermion bilinear. It was sort of assumed that, in analogy with QCD, this fermion bilinear would get a VEV, and then it would only break the SU2 flavor symmetry to U1F, and the monopole symmetry is not involved. That would only lead to 2 Goldstone bosons. And those two Goldstone bosons would just live in the CP1 base of the vibration. Now, it turns out that 2 Goldstone bosons are not even enough to match the anomalies of this theory. So that's actually not a consistent scenario. And in our proposal, the anomaly is, or the full anomaly, is matched by including the third Goldstone boson, which is the Hopf fiber over the CP1. I should say that if you dualize this Hopf fiber field sigma, you can write it as a free photon again, as a Maxwell field. And occasionally in the literature, people do say that this CP1 sigma model should be accompanied by a free photon, but it's a little bit on and off, and it's not clear what it's good for. It's not clear if it's necessary for anything, and the answer is it's definitely necessary for matching the anomalies and getting a consistent scenario.
But can you write this circle sigma in terms of psi? No, because before you said that the average of all...
No, sigma can only be written using monopole operators.
Right, but
yeah.
Not written in terms of symmetry to all.
No. No, if you take any operator that's built out of the psi's, it would be neutral under U1 magnetic, and it would not contain sigma. Yeah, you have to use the disorder operators. Yeah.
Scenario in which the two maps are not aligned with spontaneously the whole unions inconsistent.
So I'm claiming they're aligned.
Yeah, but I must know whether it would be inconsistent.
Yes.
With anomaly matching?
No, not with anomaly matching, with mass deformations and other constraints. More symmetry breaking is always good for anomaly matching. If you can match with less symmetry breaking, you can definitely match with more symmetry breaking. Okay, so since I mentioned the consistency with deformations, let me tell you some of the reasons why we believe in the scenario that I explained to you. So the first consistency check is to consider the massive theory, right? Up to now, I've considered the zero mass theory. Now I'm going to turn on masses for the quarks. And I'm going to turn on masses that live in the triplet of the SU2 flavor symmetry. There are also singlet masses, but they break time reversal, and I don't want to do that for all sorts of reasons. So I'm going to turn on a triplet mass. Now I can use the symmetry to orient my triplet mass along the z direction or the 3 direction, and so I'm going to do that. I'm going to assume that m is a positive parameter in that direction. That explicitly breaks the SU2 flavor symmetry to U1, and it preserves the U1 magnetic. Now, the moment you add such a field, right, because I told you that O gets a VEV that's aligned with the sigma model vector in the base of the Hubble vibration, when you turn on such a mass, you lift the entire CP1. So the Goldstone bosons that parameterize the base of the vibration are gapped. They get a mass that's essentially a version of the Gell-Mann-Oakes-Wenner relation for QCD, and for the pion mass. And the only thing you're left with is a single massless sigma field. Okay? So when you turn on these masses, you don't completely gap the theory. You're left with one massless Goldstone boson. And that Goldstone boson is due to the fact that this product symmetry is further broken to a diagonal subgroup. So this analysis that I just told you about was taking the massless theory, where we had the S3 sigma model, and turning on small masses. So it's like the small quark mass regime, the small electron mass regime. Let me show you what happens when you take the masses to be huge. When you take the masses to be huge, much bigger than the strong coupling scale of the theory, which is just given by the dimensionful QED gauge coupling in 3 dimensions, you can simply analyze this theory semi-classically, because the electrons are very heavy. You can just integrate them out at one loop. And at very low energies, you just get free Maxwell theory, plus lots of higher derivative terms, plus, very importantly, a Chern-Simons term that involves the dynamical U1 gauge field, little f, and background fields that couple to the U1 flavor symmetry and the U1 magnetic symmetry, which I've called big AF and big AM. And so the fact that there's this Chern-Simons term here with a particular linear combination AF plus AM tells you that the monopole operator of this Maxwell theory actually has non-trivial charges under both U1F and U1M. Because imagine that you have a monopole operator. When you integrate this F over the surface linking the monopole, then what you're left with is just a kind of world line quantum mechanics that tells you that this thing has charges 1 under AF and charge 1 under AM. So what you learn from this Chern-Simons term analysis is that the monopole that condenses at huge masses is precisely the one component of the monopole doublet. Q1, QF is 1, and QM is 1. So Q2, so M2 has to be 0, because it would have negative QF charge, and M1 is non-zero. So you see that the monopole that condenses is exactly the same monopole that condensed in the small mass regime. So we now have a picture at small masses, we have a picture at large masses, and the symmetry breaking pattern is identical. So the most minimal and natural conjecture, which I actually believe to be true, is that there is no phase transition in between the small m and large m regime. That these two regimes are just smoothly connected. You have a weakly coupled massless photon everywhere, but there's no additional phase transition as you dial this mass. Okay? That's certainly the most minimal assumption, but it turns out that I can't quite prove that. I'll be able to prove something a little bit weaker than that, and that will be that everywhere in this non-zero M regime, there is a weakly coupled photon in the IR. I can't necessarily rule out the presence of additional neutral stuff, But it turns out that that neutral stuff would only interact very weakly with the photon via irrelevant operators, and it can't change these quantized Chern-Simons terms. So the conclusions that we drew essentially remain unchanged. Okay, yes?
What is the status of parity in the large mass limit? There's some wedge.
Oh, parity is everywhere a good symmetry. I actually chose my mass deformation to be such that it preserved parity and time reversal. Yeah. The reason why this Chern-Simons term is okay is because parity can act non-trivially on these fields. Give them a sign. They give different signs to these and this. Yeah.
There's no decoupling inflation?
There's no what?
There's no decoupling because normally I would be thinking that the limit of large M.
Emphatically, there is no decoupling in that sense. So in the limit of large M, I'm left with a massless particle, the photon. I'm claiming that photon is there for every non-zero value of M. So when you turn on M, you don't get a gap theory. So this is a major difference with... It is decoupling. It's just that the quark, the electrons decouple, but you're left with the photon. And the photon is massless. So this is not... The reason it's different in QCD is because decoupling also happens, but then you're left with pure Yang-Mills theory, which confines. Here you're left with pure Maxwell, which doesn't confine. All right. So let me briefly outline the argument. The argument is essentially a version of the QED inequalities or the QCD inequalities a la Weingarten and Waffa and Witten, essentially using the fact that the electron propagator at positive M is exponentially decaying in the presence of electromagnetic background fields, and also using the fact that the mass deformation I chose preserves the positivity of the functional integral measure. You can argue that any operator that creates an electrically charged composite has to be exponentially decaying at long distances. And so what this shows is that for finite M, there's a gap to charge degrees of freedom. There's a charge gap. So all electrically charged things are heavy, and the only thing you could possibly get in the infrared are electrically neutral. And well, in the interest of time, maybe I'll just say this quickly, but once you have a charge gap, that's sufficient to ensure that the weakly coupled photon emerges in the deep infrared. One way to say it, maybe I'll say it in this language, is that the photon in Maxwell theory is protected by the fact that there's both a magnetic symmetry and a center symmetry, an electric one-form symmetry, and they have a mixed anomaly. And you can think of the photon as the masslessness and the freeness of the photon as a Goldstone boson is coming from those facts. Now in QED, you don't have the one-form symmetry because the electrons are charged and they explicitly break it. But the moment you know that there's a charge gap, then you know that at long distances below that gap, the one-form symmetry will emerge and the massless photon will come back. As I said, there might also be other electrically neutral degrees of freedom that I can't necessarily control, but since the photon is a Goldstone boson, it will only couple to them very weakly. Okay, in the interest of time, let me make this quick. So we've established that at finite mass, which I can take anywhere in the isospin plane, there's symmetry breaking with a monopole that's aligned with a mass vector in a way that's governed by the Hopf map, okay? And since I've told you that this symmetry breaking phase is there all the way to the origin, you can then take the M going to zero limit and essentially recover the symmetry breaking pattern that I argued for. You have to rule out a couple of alternative possibilities. If you want to know more about that argument, I'm happy to talk to you in more detail, but in the interest of time, I'll move on. Let me just say that these alternatives can be ruled out. And so this provides strong evidence for our scenario. Let me say a word about how you might probe this scenario on the lattice. So of course, the whole story was about symmetry breaking, and both of the symmetries involved a challenging. There's an SU2 symmetry acting on the electron fields, and that SU2 symmetry is in a certain sense chiral, right? It's not vector-like, it's not compatible with the Dirac mass. And so that in and of itself needs to be taken care of using a formulation where that chiral symmetry is good on the lattice. But here you have the additional problem that the symmetry breaking is also driven by the U1 magnetic. So you need a lattice formulation where the U1 magnetic is good or not too badly broken. You could imagine something like a modified Villain formulation that enforces that, but the problem is that that might introduce a sign problem due to the Lagrange multiplier fields. Doesn't always, but in principle it can. There's an interesting variant of this theory that sort of gets around this problem, which I wanted to mention. It's also kind of cute, which is you can, instead of studying the theory with gauge group U1, you could take the gauge group to be non-compact. You could take it to be R. Roughly speaking, the way to go from U1 to R is to flatly gauge the U1 magnetic symmetry, meaning you only integrate over flat U1 magnetic connections, but not non-flat ones. Now, whenever you do such a flat gauging, the theory that you get is locally identical. So the theory with our gauge group would still have 3 number Goldstone bosons, but the symmetry breaking is a little bit more funny because the monopole operators, which were standard local operators in the U1 theory, are no longer local operators. And that, in fact, that's a good thing because that prevents them from showing up in the Lagrangian and ruining the U1 magnetic symmetry, which is now gauged. So how do you detect the symmetry breaking that is allegedly due to these non-gauge invariant or non-local operators? Well, the way in which these operators become non-local is very mild, right? They're essentially attached, because you flatly gauge the U1 magnetic symmetry, they're attached to a flat Wilson line of that U1M symmetry. From the point of view of the theory with our gauge group, you can think of that Wilson line as the generator of the one-form symmetry that that theory possesses, and it's a bit of a funny one-form symmetry. It's called a Z one-form symmetry. And so then you can make a gauge invariant bilocal order parameter where the non-locality is only in this very mild topological line. So these are sometimes called string order parameters, and you could look for such a VEV in the clustering limit when x and y infinitely separate, and that would be visible even in this R version of the theory. So that's something that I wanted to mention. Alexei tells me I'm out of time, so unless somebody asks me about it, I will not say anything about supersymmetry now, although I hope somebody will ask me about it. And let me summarize. So I talked about massless QED with a minimal non-trivial number of flavors, 2 flavors, and I told you a story that starts from the assumption that this theory is not a conformal field theory. I told you that that was suggested by the bootstrap, and if I have time, I might also tell you why it's suggested by Suzy. And in that theory, I've proposed a symmetry breaking scenario like this, where the flavor symmetry and the magnetic symmetry are sort of non-trivially broken to a U1 subgroup by this fundamental monopole doublet. And then it turns out that the fermion doublet, the fermion bilinear, which is the sort of more standard order parameter, is like a kind of a secondary object. It also gets a VEV that's precisely aligned with the monopole VEV, but it's not the sort of primary driver of the symmetry breaking. So instead of 2 Goldstone bosons, you get 3 Goldstone bosons in this squashed S3 sigma model with the theta term that's needed for anomaly matching. So maybe I'll stop here. Thanks.
Thank you for a wonderful talk. We have time for questions.
Sorry, I'm not going to ask you about supersymmetry. I'll have to wait for somebody else. I was wondering if you could take the 4-flavor model and change the relative charges of 2 of the flavors compared to the other 2 and interpolate between your theory, when you take one of the charges to go to 0, and this conformal point when they're all equal. Would there be a phase transition in between there?
Well, in the U1 theory, the charges are quantized.
Yeah, so this would be an R theory.
Yeah, you could imagine taking an R
theory. Or you
theory.
could do a sequence of quantized
I think that's an interesting question that, to my knowledge, has not been explored. So I think in the R theory, there's kind of a new interesting continuous parameter, which is exactly what you said, which is the sort of relative charge of all the fields. Right. Because the sort of absolute charge doesn't really make much of a difference. And maybe there's some new version of an epsilon expansion or something like that. I think that's sort of what you're asking, right? Yeah. I haven't thought about, well, I've thought about it to the extent that
it seems like it's conformal on one side, according to what you said, the 4-flavor, and then it's spontaneously broken on another side. So there must be some kind of phase transition in between.
Yeah. The question is whether you can actually do computations, because I mean, in principle, both of the endpoints are strongly coupled. So just continuing in the charges by itself doesn't make the theory computable. But yeah, I think it's interesting.
More questions? Oh, okay.
So actually, we're looking at this in radial quantization on R cross S2. So if you start with 4 flavors, presumably it's a conformal field theory.
One guesses.
Most people believe, right? And then it's perfectly okay to go to radial quantization.
Yes.
Now, if it's not conformal, is that disallowed? In other words, if this is conformal, what does not go through in your analysis? It totally changes the situation if it's conformal?
Well, there's no symmetry breaking in that case. So the difference will be, there's nothing wrong with going to S2, it's just that you'll see different signatures. So
you still could go to R cross S2.
You can do that,
but you would see
in the conformal case,
theory,
you'll see like gaps that are consistent. You'll see sort of a gap spectrum that's consistent with conformal symmetry that organizes.
And so then the
in a
volume
tower.
Dependence of the sphere would drop out as a finite volume.
But here it wouldn't, and so you would get kind of finite size volume scaling that reflects the physics of the Goldstone bosons.
Okay, but then the massive states would be okay, right? But you could still get the same physics on R cross S2?
Yeah, I mean, you could do a version of you could use the S2 just to do like finite volume scaling to see the Goldstone bosons if you wanted to. Yeah.
Yes, I recall that about 10 years ago or so, there were a lot of lattice calculations looking at this model.
Yeah.
2 flavors, 4 flavors. I don't remember the conclusion, but do you?
Yes. In fact, I briefly referenced one of them. I was going too fast to point it out explicitly. I mean, this has been studied by many authors, but I think this is the group that was working in that time frame. I think that at the time, there were indications and arguments that the 2-flavor theory might flow to a CFT. Those were not definitive. They involved a lot of assumptions, but there was something nice that would happen if this theory did flow to a CFT involving enhanced symmetry and so forth. But that motivated people to actually look for a gapless point without symmetry breaking, and at the time, these papers seem to indicate that what they're seeing is consistent with that. Well, now what I'm telling you is that I think this thing is not a CFT, and it probably breaks symmetries, and whatever they didn't see any evidence of it. But it's very possible that, the lattices weren't big enough, and I mean, there's always...
I did work on this at the same time. We never published because we wanted to monopolize this.
Okay.
So I will talk to you after.
Yes, please. Yeah. I'm saying, I think what was done then was not conclusive, and it would be nice to revisit it.
Yeah. I had a related comment, but going back further to the past, John Kogat, of course, and collaborators did a lot of work on non-compact QED and found pretty strong evidence for non-zero VEV in the
bilinear VEV.
In the 2-flavor case.
Bilinear VEV, though.
And
bilinear VEV, fermion.
Yeah, bilinear VEV. And no VEV in the 4-flavor case, which is the first one where there is no sign problem due to the doubling, I think. Yeah, so yeah, it would be great to revisit the story, I think. Yeah, just one more comment. I think more recently with domain wall fermions, again, I'm far from knowledgeable, but Simon Hands did the domain wall case and claimed he also sees the bilinear VEV in the 2-flavor case, I believe.
Steve, a question?
Yes, was next. Yeah.
I mean, so naively, let's talk about the case where the gauge group is R. So roughly speaking, you have this rather strong Coulomb interaction between the fermions, right, and that's rising. What happens if you add a tiny mass term to the photon, which is perfectly allowed for the non-compact?
In this case, what?
Just a mu squared, mass term.
That's not allowed. That's not allowed in the non-compact theory, right?
Why not?
Because if you insist that we're still insisting on R gauge invariance.
Yeah, but don't insist on R gauge invariance. If the mass is 10 to the minus 10, it would be unbelievable if you didn't get the same physics.
Fair, yes.
So do you have a phase diagram as a function of the mass of the photon?
Well, I think if you give the photon a mass, you trivialize all the anomalies.
But nonetheless, you have Coulomb interactions up till very long distances.
That's true.
It would be very surprising if the phase diagram of the theory isn't the same if the mass is 10 to the minus 10.
Well, the only difference, I think I intuitively agree with you. You mean as far as the binding of the fermions?
Yeah, yeah.
Right. But the only thing that will happen is that in the asymptotic phases, I have a gapless photon, and now it'll have a tiny mass.
Yeah, but you might imagine that there's a phase diagram. When you make the mass big enough, like it's not strong enough to bind the fermions, and so you might have an interesting phase diagram.
Yeah, so if the mass is much bigger than the strong coupling scale, you might imagine something.
That's right. So that would be just another knot.
Even that's not obvious. You might get some sort of charmonium type.
Exactly. So, but it seems like there's another dial, since the physics is essentially perturbative.
Mm-hmm.
Okay, we have several more questions. So one second.
Isn't this what is the Turing model, 3D Turing model? I think people studied it numerically very extensively. Well, they just add a mu squared.
Yeah, but you also have
in the non-compact.
No, but I also have f squared.
Yeah. That would be,
they just add a mu squared.
Yeah, it's a long distance for fermion. It's a non-local for
fermion. Right, but there is some regime, I think.
Large mass.
The large mass, yeah, okay.
A question from Silvio in the back.
So these QED theories are sometimes argued to appear as emergent descriptions of spin systems. Mm-hmm. Does this pattern of symmetry breaking have any implications for such descriptions?
Broadly, absolutely.
Do you know any specific example?
There are surely experts here that know more about it than I do, but my impression was that the case that's of more interest is the theory with 4 flavors, mm-hmm. Which is still conformal, right. So that story wouldn't change. But yeah, I think there are presumably systems that in one way or another involve the 2-flavor case as well, and they need to be reanalyzed in light of this. Yeah. One thing I should say though is that in those systems, generically, you always break the monopole symmetry to either nothing or to a very small subgroup. And the moment you know that, then the system becomes kind of gapped anyway and flows away from this phase. So in order to have my story, you need to flow to this massless point while tuning the monopoles to 0.
Are there applications for cosmology? High temperature, 10 MeV, you have.
Well,
or the electron becomes
as I said in the beginning, this is also basically high temperature QED. So
that's what I'm saying. Yeah.
Although this QED would further break the SU2 symmetry, of course, to the U1 axial, but that's okay. There will be still something.
There's a nice paper by Tharun Grover constraining the conformal window of QED by the F theorem. Did you check that your scenario is consistent with it?
Nobody, many people have bounded this bound of the conformal window. My impression was that nobody ever definitively said whether it was 2 or 4.
That's correct. So
everything is sort of consistent with being in that range.
But the idea is that monotonicity of F constrains the infrared physics. Yeah. Right? So are your 3 Goldstone bosons consistent with? It must be.
There's always said that when an F is bigger than 8, it's definitely conformal.
Actually, I think Igor checked the F theorem in this case. Yeah, also, yeah. And you guys certainly included the photon. I don't remember about Tarun's paper, but you guys certainly included the photon, yeah.
So we have one last quick question from Arkady, and then we have to move on.
You're giving me a threat. First I'd like just to add about the suggestion for photon mass. You can have this like a Higgs mechanism without breaking any gauge invariance, adding another charge field. Right? This you can do, and it would be a spontaneous breaking, due to this charge field. But not just to leave it gauge invariant. But my question is about this decoupling. I understood what your point about this appearance, but I was thinking that if you have this extra, like an extra particle, surviving at, say, 0 mass or whatever, then I would think that having large but finite mass would reflect in some kind of the core of the particle. There should be size inside of the particle which would diminish with increasing m. So it should be some like a fun factor, whatever, which depends on this m at large m still. You see what I'm trying to ask about, that this monopole type of, this is related to monopole breaking should show up this m dependence in terms.
Are you talking about the fermion mass m?
Sorry?
Are you talking about the fermion mass m now?
No, about this composite kind of new state which you are discussing, that the fun factor of this state should be reflecting, large m. Because you are talking about that besides this normal Gauss-Thorne, you have additional one, right?
Right.
And I'm talking
so yeah,
about,
if you write some sum rule or something, you have to include it, yes. I haven't thought about it, but yeah, it would be interesting to think about.
Okay.
All right. I think we need to move on to the next talk by Shuheng. So let's thank Thomas again.